Hello everyone. Welcome to my talk on optimal design of Evtols for urban mobility using analytical target cascading. Most of the work for this project was done at Poets Research Center at University of Illinois in Urbana-Champaign. I worked on this project along with my colleague Ganendra Das, and Professor James Allison and Professor Kai James have been guiding me on this project. Let's quickly look at the motivation for this project. The use of vertical takeoff and landing aircraft has many advantages. The first advantage is that it has a comparable cost per flight when compared with conventional mode of transport. It has the capability of utilizing vertical space for transportation, which is lacking in conventional mode of transport when we are considering urban mobility. And it also can be operated in an environmentally friendly fashion because these vehicles are battery powered. The development efforts for these aircrafts are in early design stages, which means that there is plenty of scope for optimizing the overall design of the aircraft. Um, However, the optimization methods that are currently in place today lack the modularity and flexibility required for optimizing an engineering problem of this scale. Um, Multidisciplinary optimizations techniques, or we'll shortly refer to as MDO from now on, um, ha- aim to solve this kind of problem by making this problem formulation more flexible and modular. And in this project, we'll be looking at one such MDO technique called analytical target cascading. So, what is multidisciplinary optimization? Multidisciplinary optimization optimizes multiple disciplines and systems while capturing all the synergies between them. So if you look at the system towards that is depicted in the right hand side, you see that this is a optimization of an aerodynamic wing. In this problem, we are trying to optimize the wing structure for a particular objective function. So that can be something like the overall mass of the wing or the lift by drag ratio of the wing. So for calculating these objective functions, we need to perform two different kind of analysis. The first one is the aerodynamic analysis, which takes in the shape of the wing and gives out the aerodynamic forces acting on the wing. On other hand, we also need to perform a structural analysis, which takes in the forces acting on the wing and gives out the deformed shape of the wing. So as you can see, these both these analyses are interrelated or we could say coupled. And this is the reason why if you want to optimize a system like this, you need to consider the synergies that exist between two different disciplines, or it can also be two different components or subsystems. So broadly, multidisciplinary optimization methods can be classified into two different kinds. The first the first kind is called the monolithic MDO or a single level MDO. And the key feature here is that it uses only a single optimizer for the entire problem formulation. And because it uses a single optimizer, these kind of methods are not as modular or flexible. On the other hand, we also have distributed MDO methods or multi-level MDO methods, where we use multiple optimizers and it can be formulated in such a way that we can use individual optimizer for each different discipline or subsystem. And because we are using individual optimizers, we have the flexibility of using whatever optimization algorithm we want for every discipline. So, and apart from that, these can also be more modular, and that makes it more compatible for implementing these methods in engineering practice. So the multidisciplinary optimization method that we are looking at in this problem is called analytical target cascading. So this method is basically a hierarchical distributed MDO method. And the reason why we are choosing this method is because this method actually emulates engineering design practice. So as you can see on the image on the right, the structure is it follows a tree-like structure where each node communicates only with its parents or its child nodes, and hence the information flow is more structured. And each node actually has its own copy of design variables, and at the end of each and every iteration of this algorithm, we try to update the penalty function so that after each and every iteration, all the nodes or all the design variables of each nodes are much closer to each other. So the algorithm itself follows the steps that are shown in this slide. Um, First is that we need to input a set of initial design variables, and once we define these design variables, we need to immediately jump into the disciplinary optimization, where we formulate the entire discipline optimization problem. So that includes formulating or computing the discipline objective function, the disciplinary analysis and function, constraint functions within that discipline, and the penalty function values. So once all these quantities are formulated or calculated, the optimization algorithm is run, or we use an individual optimizer to optimize for this formulation. And then this process is repeated for all the other disciplines as well. So once all the disciplines are covered, we initiate the system optimizer, where we similarly formulate the system level objective function, the constraints, and all the penalty functions, and the system level optimizer is solved. So once the system level optimizer is solved, we finally take in all the design variables existing in each and every node, and based on the difference of difference that exists between different design variables or different copies of the same design variable, we update the penalty weights. So if the design variables are far apart from each other, we make sure that the penalty weights are increased sufficiently so that in the next or subsequent iteration, the design variables or the local copies of the design variables are forced to be much closer to each other. And this process is continued until all the design variables converge to the same value, or all the local copies of the design variables converge to the same value. And once that tolerance is reached, the ATC algorithm is stopped, and the final set of design variables that you end up with are the optimal design variables according to the ATC algorithm. Coming to the implementation of ATC on eVTOL design, the problem that we are trying to solve is to minimize the mass of the aircraft, given that it has to carry a specified payload, and it has to do that for a specified range, and the flight planning is done according to a simple mission which is laid out on the image on the right hand side. So the first phase of the flight is basically to take off and ascend to a particular height. In this phase, the motors run at maximum power so as to ensure that the thrust provided by the propeller is greater than the weight of the aircraft. And this is immediately followed by the transition and acceleration phase, where the aircraft accelerates to a particular cruise velocity. And this is followed by the cruise phase, where the aircraft covers the given range in the on that in the particular cruise velocity that is determined by the acceleration phase. And then this phase is followed by the transition and deceleration phase, and then this is followed by the landing phase. So the subsystems that we are considering in this problem formulation are the motors, the wings, and the gearbox. So the motor, for the motor, we are using a torque efficiency and RPM map, so that we can determine the RPM point. Based on the RPM point and the operating torque point, we can determine what the efficiency of the motor is going to be. And for the wing subsystem, the functionality of wing subsystem is to compute the overall lift that is generated at a particular cruise velocity, and it does so by using nonlinear lift theory. And finally, we have the gearbox subsystem, which uses an empirical sizing model based on the torque that the output torque of the gearbox. It determines what should be the mass of the gearbox. And the key design parameters that we are looking at in this entire problem formulation are component masses, RPM at which the motors need to be operating, and the cruise velocity of the aircraft, and finally the wingspan of the the wing of the aircraft. So the detailed formulation for this problem is shown in this picture here. So here we see that there's a system level objective function where we are trying to optimize for the mass of the vehicle, subject to a few constraints. So the first constraint is that the energy that it consumes for the reserve mission must be less than 95% of the energy that is stored in the battery, and the mass of all the components put together must be less than the maximum takeoff weight of the aircraft. And finally, the power that is required during the ascent phase must be less than the motor power. So here we are optimizing for a lot of design variables. And as I mentioned, there are a few key design variables included, um, so that we can understand how these design variation of these design parameters affects the overall mass of the vehicle. And coming to the different subsystems that are used in this formulation, so the wing subsystem basically uses nonlinear lift theory to generate or to compute what is the lift that is generated during flight. And the constraint here is that the lift that is generated during flight must be greater than the weight of the aircraft. And the objective function here is the augmented Lagrangian penalty function. So this penalty function just ensures that at the end of each and every iteration, the local copy of all the design variables are um, closer to the system level uh, local copy of design variables as each and every iteration progresses. And similarly, all the other subsystems also have the same augmented Lagrangian penalty function as the objective function. And coming to the motor, the functionality of the motor subsystem is to generate the efficiency or compute the efficiency at a given RPM and torque point. So the the constraint here is that the overall efficiency of the motor is basically equal to the efficiency that is computed from the RPM torque and efficiency map of the motor. And in the gearbox, finally, we have uh, one constraint, that is the torque base sizing of the gearbox must be less than the actual mass of the gearbox, or rather the mass of the gearbox must be greater than the sizing that we determine. So this slide shows the results of running ATC on this eVTOL formulation. So the y-axis here is the mass in kilograms, and the x-axis is the range. And in this graph, you can see that there are two different bar graphs that are stacked right next to each other for each range point. And the first, or the bar graph that is stacked on the left, are the results from monolithic architecture, and the bar graphs that are stacked on the right are the results from ATC architecture. So, and each color highlights a different component within the eVTOL system. And basically, the conclusion or takeaway from this study is that um, ATC actually converges to something very similar to what you would expect from monolithic optimization formulation. So yes, coming to the conclusions, we have the first conclusion is that the ATC algorithm converges to the same solution as a single level optimizer. And one caveat here is that ATC algorithm, while it converges to the same value, requires a lot of tuning of different convergence rate parameters, and it also requires more function evaluations as compared to monolithic architecture. And the whole point of using ATC here is not to make the algorithm more efficient, but to make sure that these kind of algorithm can be more feasible for utilization in engineering practice. So if you take a conventional monolithic architecture, it is not modular or flexible enough for usage in engineering design practice, while ATC algorithm gives you the flexibility to use whatever optimizer you want for each and every discipline. And it is also more easy to add or remove subsystems or change the fidelity of each subsystem with an ATC formulation. And another byproduct of this project was that we developed a generalized MATLAB application wherein you can enter the different objective functions, and it'll run the ATC formulation for you and give out the results of the optimal design variables. And as I already mentioned, ATC formulation is more modular, and hence adding new subsystems, changing the fidelity of existing modules is easier as compared to monolithic architecture. So these are some of the references that were helpful for me to execute this project. And finally, I would like to thank National Science Foundation for funding this project, and the Poet Center, as well as NASA for their guidance. And if there are any other questions, I can take them up right now.